Uh, it's really an honor to welcome Bill Henshaw to our finite element seminar at Livermore. Bill is a distinguished professor at RPI. He got his bachelor at Waterloo, then did PhD in Caltech, and then worked in a lot of really impressive places, the IBM Watson Center, Los Alamos. And I know him from when he was at Livermore. He's done a lot of work on solving PDEs, particularly on overlapping grid. He's the primary developer of the Overture framework. And today he's going to tell us about WaveHoltz, which is this interesting approach to solving Helmholtz by filtering in time the wave equation. So it's a real pleasure to have you, Bill. Floor is yours.
Thank you, Sonia. Yeah, so I'm going to tell you about, so I've been learning about Helmholtz problems for the last few years. And so I'm going to tell you about this new algorithm and some of the things I've learned about solving Helmholtz problems, which can get really hard. So first of all, oops, does that work? So here are some of my collaborators. So I worked with Jeff Banks. Jeff was actually at Livermore for a number of years when I was there, Don Schwindeman, and we have a student, Non, who's a grad student, and we work closely with Daniel Papello, who was one of the originators of the WaveHoltz algorithm. So what's the motivation? So as probably many of you know, Helmholtz problems arise in many areas for wave propagation problems, looking for time periodic solutions, solid mechanics, acoustics, electromagnetics. And our interest, one interest for us is in time domain Maxwell's equations. So we have developed some high order solvers for dispersive Maxwell's equations on overset grids. And well, I should say here, if you have questions, please go ahead and ask questions anytime. Unmute and ask a question. So the question is, so if you have a time domain solver, the question is, suppose you have worked hard to get a nice time domain solver, can you turn it in to find Helmholtz solutions, that is time periodic solutions? So how can you use this time domain solver that you've written to do that? And a lot of the publications, as Sonia mentioned, I've developed this Overture framework, and a lot of the publications can be found under publications in overtureframework.org if you're interested. So here's the basic question. I'm going to step back and just do the wave equation, right? So eventually we want to do Maxwell's, but we're going to do the wave equation. So here's the basic question. Suppose I solve the wave equation in this domain here, and I have a periodic forcing. So the question is, if I just do this periodic forcing and integrate for a long time, will it go to the periodic solution? Well, in this case, I have Dirichlet boundary conditions all around, so it's an energy conserving problem. So the answer is no, it will not go to the time periodic solution. So we need to do something else to make it go to the time periodic solution. Because on the right here, this is the actual time periodic solution. And one thing you learn, especially at high frequency, if you look at the time periodic solution, you cannot really tell where the source is, right? You remember from the video, the source was sort of in between those triangles, but from the Helmholtz solution, it's really hard to tell. So just to give the answer away, so we can use this WaveHoltz algorithm. It uses the time domain solver and then does a certain time filter. And by doing that, we can converge to the Helmholtz solution. And in this graph, we'll talk more about what's actually showing here, but where I say iteration on the bottom, the iteration corresponds to each iteration corresponding to solves the wave equation over some number of periods and then filtering. Okay, so each iteration is to solve a wave equation over one or more periods and filtering. And I'm showing results here for the fixed point iteration and GMRES and some theory. So how do we do this? Whoops, need to click here. So our goal is to find time periodic solutions to PDE problems. And there's enormous amount of work that's been done on solving Helmholtz problems, including boundary integral methods, fast direct solvers, domain decomposition methods. The basic takeaway, though, is for really large problems, we have to use iterative methods those are really hard. And there's this nice paper at the bottom by Gander saying why, if you're just used to solving Laplace equation with GMRES, it's always going to work, right? And you do a Helmholtz problem, well, GMRES is not working very well, really not working very well. So some of the issues are problems get really hard at high frequencies. There's something called pollution errors I'll talk about, dispersion errors. You need potentially really fine grids, or this is where you can really make use of higher order methods. And so there are sort of specialized Helmholtz solvers that don't, and there are some specialized ones that work really well, but maybe they're limited in their scope. So here's the algorithm. So the goal is to solve this Helmholtz problem here. L is c² Laplacian, and omega is a given real number, that's the frequency, and we have some forcing on the equation and potentially on the boundary conditions. So what we do is we solve the associated wave equation, where now we have multiplied the forcings by cos omega t. Okay, so in these wave equations, we have cos omega t, and we're going to iterate. In this case, we're doing what I call energy conserving problems, or with like Dirichlet boundary conditions. We'll treat radiation. We'll treat sort of open domains with radiation boundary conditions later. So in this case, the algorithm is a little simpler. We can just iterate on the initial condition. So the initial condition, I denote V of k, where k is the iteration number. We're going to solve the wave equation with our current guess, and this Vk is going to if it works, it's going to converge to U, the Helmholtz solution. Okay, so we solve the wave equation, get the solution over time, and then we apply it to get the new iterate, V of k plus 1. We're going to apply this time filter to W. So this time filter, which involves a cos omega t, is going to sort of damp all frequencies away from omega while leaving frequency omega in the solution unchanged. Okay, so that's the basic idea. So the basic idea of WaveHoltz is quite simple, right? You just need a time domain solver and you need a filter. But then there are lots of details to get everything working nicely. So here's the algorithm. Just reiterating what I just said, right? So you have some loop over iteration k. You solve the wave equation, and then you apply a filter, which in the discrete case could just be like a quadrature rule, like trapezoidal rule. So in practice, you don't need to store the solution at all time steps. You would, on line 6, you would accumulate that quadrature as you take a time step. So that's the basic fixed point iteration, and there's some references down below. The first reference by Apello, Garcia, and Runberg, that's sort of the initial WaveHoltz. That's a nice paper describing the WaveHoltz algorithm. And then they have, Daniel and the collaborators have extended that to electromagnetics, to elasticity. And then the last one is a paper now in revision describing extensions, developing the algorithm on overset grids, and also some extensions leading to this order n algorithm. So what's going on here? So the WaveHoltz algorithm, this steps of starting with initial condition Vk, integrating in time the wave equation, and filtering can be written in this operator form. So the new iterate is some operator A times the old iterate plus B, okay? So the interesting thing here is that this operator, which in the discrete case, we never form that discrete operator explicitly, right? We just know how to apply it. So the nice thing, it has the same eigenvalues as the Laplace operator. So I'm going to denote by phi j and lambda minus lambda j squared, the eigenvalues and eigenvectors of the Laplace operator. So A has the same eigenvectors, but it has different eigenvalues. So we've done a spectral transformation here. And what are these new eigenvalues of this A? Well, they're this filter function in the lower left evaluated at so the filter function is now being applied to cos lambda t, where lambda here is just any value of lambda. But then the eigenvalues, you evaluate this filter function at each of the eigenvalues of the Laplacian. So if we plot the filter function data, it's actually a sum of 3 different sinc functions. There's a sinc function at 0, a sinc function at omega, and a sinc function at minus omega. So that's this blue curve. And on this graph, I've marked some points, red points, and those represent, say, the eigenvalues of a 1D Laplacian, right? So the red points go off to infinity over to the right. But then if we look at the eigenvalues of this scripty A operator, they're in green, they go up the vertical axis. So it's transformed all the original eigenvalues, which go off to infinity, to all lie within minus 0.5 to 1, right? And so there's a lot of eigenvalues near 0, and then there's in terms of the fixed point iteration, the problematic eigenvalues will be the ones near 1. Right, but that's sort of the key thing here is we've done this transformation, so it's an easier problem to solve by standard methods. So that's sort of the key thing. And so the basic fixed point iteration, which we'll talk about improving it, is the basic result is that the fixed point iteration will converge as long as we're not forcing the Helmholtz problem at an eigenvalue, so we're not at resonance. And the convergence rate will be given by the worst beta sub m, beta of lambda sub m, right? So in this picture I've shown down at the bottom, the asymptotic convergence rate will be this green point near 1, right? So it's going to be relatively slow, and we have ways to improve it, but that's the basic result, right? So if we're not at resonance, it will converge, although maybe slowly. So this is sort of a key figure to see here. We're going to see other plots of this beta function or relatives of it. And the key thing is, at least for the fixed point iteration, the slowly converging modes are the ones where beta is large in magnitude. So there are various ways to enhance the basic algorithm. One is to use matrix-free Krylov methods, such as GMRES or conjugate gradient. So we'll talk about that. Another interesting thing, which was really surprising when we first saw it, so you can do implicit time stepping on the wave equation, which maybe normally you wouldn't do on the wave equation. And not only that, but you can take a huge time step. And the algorithm still works, right? So that's sort of very unusual for wave equations, taking a huge time step with implicit time stepping. But that's one key to get this order n algorithm. And then you can do something called deflation, which is like a preconditioner, using pre-computed eigenvalues and eigenvectors. So I'm going to talk about each of these 3 different enhancements. So how do we do time stepping? So we're using finite differences, but you could do WaveHoltz can be used, has been used with finite elements, DG, and all sorts of things, right? But in my mind, I'm thinking I want to do overset grid. So we're doing some approximation to the wave equation. Turns out we only need second order accurate in time because we can fix up the errors in time. But we use some higher order difference in space, denoted here by LPH. And then we have some forcing, and in order to correct for the sort of dispersion errors due to the time difference, there's some tricks you can play by adjusting the forcing. You can sort of adjust the frequency that you actually solve the wave equation for, so that when you get the Helmholtz solution has the correct omega, right? So our sort of goal here is to converge to the corresponding discrete Helmholtz solution with the correct omega, right? So you can play some games and make that work. It's quite easy to sort of fix the dispersion errors due to time. And the key thing here is when we do implicit time stepping on the wave equation, the matrix you need to invert down here is M. It's sort of a definite Helmholtz problem, right? It's I minus delta T squared times Laplacian, right? Laplacian has like negative eigenvalues, so that's like a positive operator there, right? So that's what multigrid was designed to solve, right? That's even easier than Laplace equation, right? So that's that. So even though with implicit time stepping we have to invert a matrix, it's a definite matrix. In contrast, many algorithms for Helmholtz have to solve a large, sparse, indefinite matrix, which is really hard to solve by iteration. But we don't ever have to do that here. And well, you can do it. I mean, both implicit and explicit time stepping could be useful depending on the regime. Explicit time stepping might be faster. But amazingly, it turns out the algorithm still works even if you take 10 implicit time steps per period, independent of the mesh size, right? So you refine the mesh, you just have to take 10 steps per period. So you have a huge time step, huge CFL number that you're running with, but it still works, which is really amazing. Now we can also accelerate the WaveHoltz operated with Krylov space solver. And so the actual linear system, before I'd written down the fixed point iteration, right? The fixed point iteration will converge to this equation I've written here. So the matrix involved that you really actually want to solve is not involving A, or here I've written AH, which is some matrix now, discrete approximation to A. The matrix you want to solve is the identity minus this AH, right? So that's what GMRES is trying to solve. And we never form this matrix A sub H, but we can apply it by doing a wave solve and a filter with zero forcing. That's how you apply the A. So now you can use a matrix-free, you can use conjugate gradient if you have a symmetric discretization. On overset grids, we normally don't have it's close to symmetric, but it's usually not. So we use something like GMRES or by CG stab. And so in terms of convergence for Krylov space solvers, you sort of want, instead of looking at the beta curve, you want to look at 1 minus beta, because those are the eigenvalues of I minus AH. So you can see here in this plot in the lower right, we get a nice clustering of eigenvalues near 1, which is good for like GMRES, right? GMRES likes clusters. But the difficulty are the eigenvalues near 0, where lambda is close to omega, right? So just like the fixed point was hard when lambda was near omega, GMRES is sort of being slowed down by eigenvalues near omega. But one way to improve it is to sort of precondition it by effectively removing those bad eigenvalues near 0 from the problem. And we call that eigenvector deflation. And first I'm going to talk about what we call direct eigenvector deflation. So you can pre-compute some eigenvalues and eigenvectors. Typically you deflate the eigenpairs when lambda is close to omega. And then there's a lot here on this slide. Here's the deflated algorithm. And there are two important changes here in blue that I've highlighted. One, before you start the WaveHoltz iteration, which is basically lines 7, 8, and 9, you deflate the forcing. So you remove the components of the forcing along the eigenvectors you know. And then the other key step at the end, so then you'll solve, it'll converge. The result you get will not include those eigenvectors, and then you just add them back in. Step 2 here, inflate the solution at the end. Okay, those are the two key steps. And while for overset grids, our eigenvectors are not, they're only approximately orthogonal. So we add step 10 here to orthogonalize the iteration to orthogonalize the current guess during the iteration. But that can make a big difference, pre-computing the eigenvectors. And you can do that and use those eigenvectors for lots of different omegas, for example. So you have to solve a lot of problems. You just have to do the eigenvectors once. So we've implemented the algorithm on overset grids. In the code I have for doing the wave equation is called CG waves. CG stands for composite grids, another name for overset grids. So it's high order finite differences for the wave equation built on the Overture framework. I've also, over the years and with students, developed a fast geometric multigrid algorithm for overset grids, so we can use that to solve the implicit time stepping equations. So they're ideally suited for multigrid. They're just nice, definite Helmholtz problems. And we have nice ways to treat boundaries, high order accurate treatment of boundaries to keep things stable. And so the combinate, well, here's some references here at the bottom for these various areas, but so this turns out leads to order n algorithm at fixed frequency. Okay, I'm not claiming that as you increase the frequency, the cost will sort of scale order n. It'll get harder as you increase the frequency, but at fixed frequency, if we refine the mesh, as you'll see, we often need fairly fine meshes, then it scales as order n. So here's actually a computational demonstration. Upper left is a square, lower left is a disk. Here's the overset grid for a disk. If you don't know overset grids, well, we do finite difference methods in complex geometry by putting down a bunch of structured grids that overlap. And lower right is the solution. And so what these graphs are showing, I'm plotting the CPU time, normalized CPU time divided by the number of grid points. So that if it's an order n algorithm, that curve should be flat. And so you can see for the square, it's basically stay near 1. For the disk, it for some reason initially goes down and then stays flat here. So that's sort of a computational demonstration that this looks like an order n algorithm as you refine the mesh. So here's a WaveHoltz example. We're solving, again, for this disk domain, some frequency 20. We have a Gaussian source in here somewhere. I didn't mark it where it is. So the solution's on the left here. The middle shows the convergence history for both the fixed point iteration, these blue, and we have the theory. We have theory that says what it should converge like, and then the red is the GMRES in this case. And this is a 4th order scheme. I'm doing implicit time stepping with 10 time steps per period, and I'm integrating over 2 periods. And on the right is what the beta curve looks like when you integrate over 2 periods. It's no longer that sort of single big bump. It looks like this. And so this plot I like to look at because it marks, so the red x's, so the actual computed discrete eigenvalues of the disk. And I evaluate this beta curve at those eigenvalues because we know for the fixed point iteration, that tells us what the convergence rate will be. Now the black circles are the eigenvectors that I decided to deflate. So I've deflated 58 eigenvectors here, which means the convergence rate will be sort of the worst case, not counting all those black circles. So this is the expected convergence rate here, about 0.615, when we see it matches this guy here. And here, in the next few examples, I'll just be doing Dirichlet boundary conditions. So these are all closed domain problems, energy conserving. So here's a slightly harder problem. It's a knife edge in a domain. I'm showing the overset grid and zooms of the overset grid. So I have 2 zooms of the overset grid. Now, this is the problem. There's a really small grid cells near the tip. And so this is the problem where the implicit time stepping scheme really shows its worth because, as I said, we can just take 10 time steps per period. Doesn't depend. We can have a super small cell. Doesn't matter, right? And so that's kind of nice. So here's the solution I'm computing. It's fairly high frequency. Omega is 100. We can see the bounds on the domain's basically size 1. And I've got some Gaussian source located here, and this is what the solution looks like. Here's the convergence with, lower left is convergence with no deflation. So with no deflation, we can see the fixed point iteration sort of starts to stall. GMRES sort of stalls for a while, but then it does okay. And well, this is a fairly hard problem. So you can see I'm actually integrating over 16 periods, 10 time steps per period. And now if we do some deflation, however, then how many I've deflated, somewhere it says how many I've deflated. Oh, down here, 64. I've deflated 64 eigenmodes, and we get very rapid convergence here of fixed point and GMRES with deflation. And good match to theory. So here's an interesting high frequency example. So there's something called the Penrose unillimitable room. So Roger Penrose someone posed the question, can I build a room with reflective walls such that if I place a source anywhere in the room, it will leave a dark or a quiet region somewhere in the room. Okay, so we talked about light, or we can talk about sound. And on the left, we show the overset grid, and we show there's 2 ellipses here in black, thin black lines, if you can see those. So that's Penrose's solution was to sort of build the room from 2 ellipses where the top ellipse is, its end is sort of situated at the focus of the other one. So then these are 2 high frequency solutions. Helmholtz solutions, the one in the middle involves a source in the lower left alcove. And in here, we sort of get this edge mode here, right? The solution just sort of lives on the edge here, left edge. While on the right, we have a source somewhere in the middle. And basically the upper left alcove and the lower left alcove are sort of pretty dark, right? It's only sort of in the limit of infinite frequency would they be absolutely dark or quiet. But these are pretty hard problems. Well, I'd like to explain. I've learned high frequency Helmholtz problems, especially on closed domains, they can be really, really hard. And basically, it's related to the fact that as you go to higher frequency, what do the eigenvalues look like of the Laplacian? Well, they get more closely and closely spaced, relatively speaking. They get really closely spaced. And in D dimensions, it's even worse, right? So in 1D, they sort of scale like the spacing sort of looks like 1 over lambda. In 3D, it looks like 1 over lambda squared cube, right? There's just a lot more eigenvalues very close to one another. So this makes solving the Helmholtz problem really, really hard. So here I've computed eigenfunctions of the Laplacian with Dirichlet boundary conditions, and I've plotted a few of them, and I've indicated what the eigenvalues are. So this one on the left is 287.62. One in the middle is 287.69, right? So it's very small relative change, and I get a completely different eigenfunction, right? And then on the right, another completely different eigenfunction. So what this means is if you force the Helmholtz solution near the left eigenvalue, you'll likely get a solution that looks somewhat like that eigenfunction, right? And if you force it near this lambda in the middle, you'll get a solution that looks sort of like that guy, or on the right, right? So small changes to omega gives you a completely different answer. And another way of saying that, we're very close to one or more resonant frequencies, right? So these are really hard problems. So I talked about direct deflation. So another way we've been looking at, which has its advantages, is to use what are called augmented Krylov solvers. So if you don't know, augmented Krylov solvers are Krylov solvers like GMRES, where you can provide the Krylov solver initially with a set of vectors that you want to put in the Krylov space, right? So some way or another, you've come up with some vectors you want to sit in the Krylov space, and then you minimize over that augmented space. Some people call them recycled solvers, recycled Krylov solvers, because one use of them is to, if you have to solve a Krylov system multiple times, then you can recycle some of the vectors from a previous Krylov solve into the new solve. Because there's information in the previous Krylov solve about sort of what are the slowly converging components of the solution. And another advantage here with this is you can use exact eigenvectors, but you can also just use approximate eigenvectors in these. You can use sort of any vectors you like, but if you want to get decent results, you want to use at least probably approximate eigenvectors. And these could come from a coarser grid or a lower order accurate approximation. And there's some references here about not all, so sometimes they're called there's a deflated conjugate gradient algorithm by Sod and co-workers. Not all deflated GMRES is really what you want. So I found there's this paper by in the middle here that is a nice algorithm to use. And then Eric Dusterlier and his co-workers have recycling by CG stab and different Krylov solvers. They have what they call recycled ones that we use. So let's compare the direct deflation versus these augmented. So here I'm solving a Helmholtz problem. Solution looks like in the row right. So I have this domain with a whole bunch of slits in it. Upper right are my usual plot of what the beta function, this filter function looks like with its eigenvalues, and the black marks I've done some deflation. So on the left we see a bunch of plots here. So the blue and green, so green is sort of sitting underneath the blue. The green is what we've done before, GMRES plus direct deflation. And then the augmented GMRES is in the blue, and we see it basically lies right on top of that. And then in the sort of the purple and the pinky colors, that's by CG stab with direct deflation versus augmented by GG stab or recycled by GG stab. So basically you can say you can do other. And there are pros and cons of doing augmented or not. But we can see it could be a good approach. The advantage here is there's fewer changes to your code, and you don't need exact eigenvectors, for example. So there are some advantages here. And we're working on a paper that discusses the various trade-offs of these different approaches. So now let's move on to open domains with radiation boundary conditions. So what changes? So for open domains, before the Helmholtz solution we were computing, it was just real value. U was real value. But now the solution to the Helmholtz problem will be complex values, have a real and imaginary parts. And so how it works is we can still solve for a real W, but we now iterate on two things. We iterate on the two initial conditions to the wave equation, right? So we iterate on sort of W and WT at time 0. So now we have VK and V dot K. And VK will sort of converge to the real part, and V dot will sort of converge to the imaginary part, modulo what I say before. But then we just solve with two initial conditions again, everything's real. And then we do two filters. Each V, so V we filter W, and V dot we filter dW dt. And then if it converges, then U will be V plus I over omega V dot. So we get the complex solution all working in the reals, right? So we don't have to solve with, we can still solve in the reals here. So the convergence theory, I won't go into it. It's slightly different. We sort of get a complex version of that beta function, which I think I'm going to call mu in the next few slides. But it has a similar form. So here's an example of using the algorithm to solve for scattering off a cylinder. This is the problem where we know that can work out the exact solution. So what do we have? So we have an incident wave coming in from the left in each of these four cases. Incident wave involves some wave number k sub x. And the outer boundaries here, we're just using Inglis-Maida radiation boundary conditions. You can use different boundary conditions, but here we just chose that. And it's a Dirichlet boundary condition on the cylinder. So this is for different values of kx from sort of lower incident wave number to quite high. So it turns out that these problems with open boundaries tend to actually be easier than the closed domain problems, energy conserving problems. And that's because these radiation boundary conditions, they sort of radiate energy, right? So there's some damping added to the system. And that damping is actually going to help us. So here, this is kind of complicated, but here I'm showing the convergence for one of the previous solutions, I think the one on the left. So on the far left, I show convergence. Now there's no deflation or anything. It's just a straightforward fixed point iteration. But then let's look on the right. So these are the eigenvalues of Laplacian with radiation boundary conditions, right? So you discretize Laplacian with the radiation boundary conditions adjusted. You have to convert the time domain radiation boundary conditions into into the frequency domain. But we'll notice here these eigenvalues, which used to lie on the real axis before, right? They used to lie on the real axis. Eigenvalues of the way we've defined the eigenvalues. But now you can see they've been most of them been shifted down into the lower half plane. And so the eigenvalues with negative imaginary part, that implies some damping when you do it in time. So then if we sort of plot, in this middle curve, I sort of plot what the beta curve would look like with no damping is this blue curve. I'm slightly lying here, but basically the blue curve sort of tells you if you had no damping, your convergence rate, your eigenvalues would lie on this blue curve, right? But in practice, these eigenvalues on the right, if I substitute them into our complex filter function, these are the absolute values of that filter function. So instead of being very close to 1, you see they're much smaller, right? So the worst case here is about 0.6 something, and that's what we're sort of seeing over here. Okay, so in this case, for that case, right, convergence is actually a lot faster in this case. And here's an example. Here's scattering off 3 cylinders. Just to show another example. However, you can make open domain problems really hard, pretty hard too. And that's if you add a resonator into the problem. So here in this domain on the left, here's the grid. So I'm going to have radiation boundary conditions on the outer boundary, but I'm going to have this resonator here with Dirichlet boundary conditions. And so there's almost a square cavity in here with a relatively small gap in here, right? So now if you send an incident wave from coming into the left at the right frequency, you can excite sort of a cavity mode, right? This is close to a certain eigenmode of the cavity by itself. You can almost recognize it's sort of like you can almost recognize that it's an eigenfunction of that cavity. And then here it's a higher frequency. Again, if you excite the incoming wave at a certain mode, then you can excite a cavity mode, much higher frequency cavity mode there. So what does the convergence look like here? Because if we made this gap really smaller, we make this gap, right? There's sort of more and more cavity modes, which are almost energy conserving modes. So here's what the convergence looks like in this case. So on the left, we see the convergence. GMRES is doing pretty well. But let's look at the eigenvalues. So now we see, so remember the eigenvalues on the real axis, near the real axis have very little damping. So now we see there's a bunch of eigenvalues with very little damping. And those correspond to the cavity modes. Okay, so those we can say are the cavity modes sitting there, most of them, could be slightly lying. And then when we look at the convergence rate, we can see that a lot of the cavity modes, they lie on this curve, which sort of corresponds to zero damping. So they have a little damping, but there's not very much, right? So these modes are going to slow down the convergence of the fixed point or GMRES. However, once sort of GMRES finds these here, some number here, whatever, then it's going to go fast because it sort of got rid of the worst guys. Okay. So in some sense, it's still easier than the closed domain, right? Because there's maybe relatively fewer eigenvalues, cavity modes. Although, you can come up with a problem, probably make it arbitrarily hard if you really wanted to. So let's talk about another thing that I learned about when I started working on Helmholtz problems, and that's what are called pollution or dispersion errors. So time domain people might call them dispersion errors, finite element people tend to call them pollution errors. So what's observed in practice is that when you're solving Helmholtz problems at high frequency, you seem to need a much finer grid than you would expect, than I would expect. And so the question is, how do we choose the mesh spacing? Is sort of the key, right? I'm a practical guy, I like to do computations. How do I choose the mesh spacing to get a certain error? And so it turns out high frequency Helmholtz problems suffer from pollution errors, right? This doesn't occur in the Laplace equation, but as soon as you do the indefinite Helmholtz problem, you get these pollution errors. So people like me, we know for solving time-dependent problems, Rice and Oliker came up with analysis of a model problem for the advection equation, where they could estimate the number of points per wavelength you need to get a certain accuracy. So the points per wavelength are sort of number of grid points you need over one wavelength. And we can see here this formula. So P is the order of accuracy, here even order. We see this nice 1 over P factor here. This AP, there's just some coefficients that come from the finite difference approximation. But the key thing here is what's in this bracket here. We have, well, here's the epsilon is the relative error tolerance we need. So the smaller tolerance you need, bigger points per wavelength you need. But also n periods is the time in periods over number of periods you integrate to get to the final time. So the longer you integrate, the more points per wavelength you need. Okay. And hidden in here is actually pollution errors, although we're not, you're maybe not used to it. So for Helmholtz problems, there's been nice finite element analysis by various people, including Babushka, where they show a fairly complicated analysis that the error in the Helmholtz problem basically takes, part of the error takes this form I've written down here. So there's a bunch of terms here. So this last term, kh to the power p plus 1, well, that's the normal error you would expect from solving the Laplace equation. Right, you need to have, what is k? So k is, you can think k is omega, right? It's the wave number. So kh is a non-dimensional number, and that's just saying you need to have a few points per wavelength, right? So that's fine. So that's not an issue. And p is here is the polynomial degree of our scheme. And then there's some k, and unfortunately they don't know what k is because of the complicated analysis. But the pollution term is this middle term. So we see and this is what causes the problem. So it really depends on the product of k times L. But if I fix k, if I fix omega, and make the domain bigger and bigger, then I need more and more points per wavelength, right? The solution still looks like it oscillates at the same rate, but if I make the domain bigger, then I need more and more points per wavelength to overcome the errors. So that's the pollution error. And it turns out, just like finite difference, you want to take a higher order. It's going to alleviate it if you take harder schemes. So in order to actually come up with a sort of a rule of thumb to follow the Krylov, we analyzed the model problem, 1D model problem for Helmholtz problems, and we were able to derive an explicit rule of thumb that's very similar to the Krylov, but now for a Helmholtz problem. So here's the points per wavelength requirements for Helmholtz problem. Has a similar form. There's some prefactor here. The coefficients are slightly different. But sitting in here is, instead of the time in periods you integrate to, it's the length of the domain in wavelengths. So it's how wide the domain is in terms of wavelengths. And epsilon, again, is the relative error tolerance. So it's very similar, you can see. So you can see for Helmholtz problems, you can imagine it's sort of similar to having to integrate a time domain problem. And it's the error that you accumulate as a wave propagates over the entire length of the domain. So you can think of it that way, which is, once you say it, it's maybe that's pretty natural. So here I plot points per wavelengths required for different orders of accuracy as a function of the length of the domain. And you can see here that second order schemes are really lousy, right? So if you have a domain that's 200 wavelengths wide, to get an accuracy of 10 to the minus 2, you need whatever, over 400 points per wavelength, right? And you can think of it two ways, right? You can fix the frequency and increase the size of the domain, or you can increase the frequency and fix L, and you need more and more points per wavelength. But you can see the higher order you go, the slower this growth is, right? So here's 8th order, pretty reasonable. So here's an illustration of just how bad it was, because when I first saw it, it was kind of unbelievable. So here's a cartoon of a Helmholtz. We pretend this is some Helmholtz solution, right? It oscillates a whole bunch of times, 100 wavelengths across, right? I just made this up, but you can think of it as some Helmholtz solution. Then if we zoom in, we ask, how many grid points do we need to represent one wavelength? Well, I plotted out the grid points for the second order scheme here in red. You can see there's, what's the error tolerance? 10 to the minus 2. So not that tight error tolerance. Second order scheme, you need to put in 321 points per wavelength. A whole ton of points. Unbelievable. Right? And we're not, if you come from other fields, this is not something you expect, right? If you're solving a Laplace equation, the solution looks like this. You don't need 321 points per wavelength to get error of 10 to the minus 2. So the takeaway is, of course, that you really want to use higher order methods to help eliminate this. And I should say, some methods like boundary integral methods, they don't have these pollution errors. And this is we have a paper in revision. We have a bunch of examples. This is just one example from the paper. So the rule of thumb is sometimes amazing, right? You do a rule of thumb, you do this simple model problem in 1D, you get an estimate of the points per wavelength, but then you can apply it in 2D, complicated problems, different boundary conditions, and it still seems to do a good job. So in this case, we're solving a Helmholtz problem on a disk with a manufactured solution, which is some sine x times sine y or something like that. So we can actually compute the errors. But just because of the manufactured solution, there's still pollution errors, right? So on the left, I'm showing the computed errors in blue for the second order scheme and in green for the fourth order scheme compared to the actual errors. Sorry, the blue and green are the actual errors. The black curve is the theory. The points per wavelength theory, you can sort of turn it around, and as a function of points per wavelength, you can say what the estimated error is. So you can see the black curve here is matching pretty well the true errors in blue. And here at fourth order, we get nice results, right? So again, if we pick this point, which is about, 67 points per wavelength, second order scheme, It's not a very accurate solution with 67 points per wavelength, right? So across each of these wavelengths here, we got 67 points, but it's pretty lousy. And here's what the error looks like. And the error, it looks like an eigenfunction of this domain. And here we plot, here also in the plot, I say, for some problems, we don't know the exact solution, but we use Richardson extrapolation. And this plot just shows that Richardson extrapolation can effectively give good estimates of the error. Because one of the reviewers said, oh, you can't use Richardson to estimate the error as well. You can. Okay, so how am I doing? So here's some bonus stuff. We maybe have time. I'm going to use the whole hour when I said I wouldn't there. So it turns out you can compute eigenvalues and eigenvectors with the WaveHoltz iteration. So how does it work? So you choose a target frequency omega. So suppose you want to get eigenvalues near 100. You choose omega 100. You apply the WaveHoltz iteration with zero forcing. And this provides a power iteration that actually gives the eigenvector you want, but not the eigenvalue you want. You get an eigenvalue that's basically this transformed eigenvalue, beta of lambda. But that's okay. Once you converge to the eigenvector, you can then afterwards compute the eigenvalue you want from a Rayleigh quotient. So that's very simple. And here's the algorithm. There's a lot of details here, but basically lines 5, 6, 7 are WaveHoltz. We do some Rayleigh quotient on the beta. This is like a power iteration, right? We're just doing a power iteration here, and that'll compute 1 lambda and 1 phi. And at the end, we compute the lambda we want from a Rayleigh quotient. So that's pretty simple too. So what is the advantage here? So we can choose, normally if you have to find interior eigenvalues, you can think of like the inverse iteration, right? You have to invert some big an indefinite matrix. You have to invert that, right? And a lot of methods do have to invert a large indefinite matrix, and you have to do that by iteration. Well, it's really hard, right? It's like solving the Helmholtz problem. But here we never have to invert an indefinite matrix, but we can get eigenvalues in the interior. So Daniel likes to call it like shift but no invert, right? So instead of shift and invert, we do shift but no invert, right? So there's no need to invert this shifted Laplacian, which is really hard, can be really hard to solve by iteration. Then the key thing is to make use of existing high-quality Arnoldi-based eigenvalue solvers, like the implicitly restarted Arnoldi method or Krylov solver. Sure. When we started, we tried to write our own Arnoldi methods, but we learned after a while that these high-quality software is really, really good. You do not want to try and reproduce it by yourself. And it turns out you also get an order n algorithm here. As you refine the mesh, you can compute those eigenvectors in order n. So here's the table of results for that double ellipse for the Penrose unilluminated room. And let's see, there's a lot of stuff on the table. On the left, we do second order or fourth order accurate. We've computed around 300 eigenvectors. And this has required about 760 wave solves. We're doing implicit time stepping. And so it turns out if you're willing to compute quite a few eigenvectors, then the cost per eigenvector is quite small. So the number of wave solves per eigenvector is like 2.5. And this shows that if you, in a different way, compute the eigenvectors and eigenvalues, then you get very good agreement with the ones computed in a different way. Oh, I should say, so these are pictures of some of the eigenvectors that we've computed for this thing, right? So as I said, key thing is we don't have to invert this shifted Laplacian, and we can get eigenvectors in the middle. And I've learned that the people that wrote a good, here we're using SLEPC, which is built on top of PETC. It has some nice algorithms for it, but we use it in a matrix-free fashion, which is quite easy to do. Okay, so here's the summary. So what have I talked about? So I've talked about this WaveHoltz algorithm, how you can, if you have a time domain solver, how you can turn it into Helmholtz Solver. Now, if you really want to make it fast, there's various things you can do. Implicit time stepping, use a Krylov solver to accelerate it, or do deflation. You want to use high order accuracy to overcome pollution errors. And you can use it to actually solve a variant of it. You can use it to solve for eigenvalues and eigenvectors. Here's another nice scattering problem of some shapes. And thank you for your attention. So any questions?
Well, thank you first, Bill, for this great talk. Very impressive stuff. I get some virtual applause. Okay, so I think my internet is okay, so I'll try to pose the questions. Anybody has any questions, please unmute and just ask.
Hi, Igor.
Hi, who's this?
This is Socrates.
Oh.
Here at the FEM team at the lab. Then a bit of background on wave propagation. Very nice talk. So you talked about you get age independent really convergence for a fixed frequency.
Correct.
Right out of this.
Yeah.
Is there a study on how it depends on frequency? Like, given that you overcome pollution, say you are in the regime that pollution haven't manifested yet. Let's say so you double frequency, you do one refinement, say, right?
Yeah.
Of the mesh. How is the algorithm?
Right. So we
suffer
from, well, it depends. So if you don't, we suffer from similar problems that other people have in that
is it like a linear growth on GMRES? Is it
for some of the open domain problems like I showed, scattering from an open scattering from a cylinder or something like that, there it scales like omega, right? So if you double omega,
scale size like omega, okay. Yes.
But for a closed domain, it's worse. Basically, because
when you are close to resonance, you say, yeah.
So it's more like omega to the D, or it might be omega to the D in D dimensions. So they get really hard. And so you can partially overcome it by deflating more, but if you sort of fix the amount of deflation, then currently we still have that. And so you need to work on other possible ways, like other preconditioners that people do, maybe to help that, right? But it does suffer from that. High omega gets harder and harder.
Right.
So that's a good question. So that's a common.
I mean, this is kind of expected. It cannot go away. The problem cannot go away. It has to manifest. Yeah.
Because I was pointing out, I mean, these are really, really hard. You're so close to singular problem, right?
Yes. Yes.
They are really hard problems. So if you don't sort of analytically remove them, like a boundary integral method or something, right? Then
yes, yeah.
Then it's hard.
So the cost gets higher, but Bill, is it correct that this is kind of all matrix free and scalable? So as long as you have a big enough machine, you could solve it.
Correct.
It's not like direct solve where you're limited by memory or something like that.
That's right.
You're just limited by the machine.
That's right. So that's one advantage, right? So you're solving the wave equation. You have a highly parallel solver. So it's good in that sense, right?
Yep.
So you can do large problems where direct solvers eventually are going to run out of memory.
Yep.
Okay, thanks.
Okay. Any other questions? Okay, let me ask one. Bill, you kind of mentioned it. Can this be extended to Maxwell?
Yes, well, Daniel and his collaborators have already extended it to Maxwell. Not all the features. They didn't do like implicit time stepping and things like that. So if you really want to get the order n algorithm, you have to do implicit time stepping. You need to have a fixed number of time steps per period, right? That's how we get that. But you can do Maxwell. You can do elasticity. We are working on now dispersive Maxwell because we have some solvers for dispersive Maxwell equations. But it can be extended to that.
Is it the same idea?
It's the same idea. Basically, if the solution oscillates, then you can use this filter to filter out the oscillations you don't want.
And let's say in Maxwell, you have coefficients. In addition, some materials.
Absolutely. So the advantage of this method, right? In all the problems I've showed, right, we had sort of constant C here, right? But you can have variable parameters. We do problems with interfaces and things like that. I think it's all going to go through that, right?
You don't need to take into account that coefficient in the filter somehow or anything. The filter is still
no, you don't, right? Because the filter is addressing the fact that the time periodic solution is sort of going up and down at omega, right? Independent of the material properties.
Okay.
Right. So you're shining light onto some funny material, but the light's coming in at a certain frequency, right? So the solution is going to oscillate up and down in each of the different parts of the material at omega, right? So that's why you're not going to get changes there, I don't think.
Interesting. All right. Other questions?
Yeah, I'd like to ask a question. This is Dylan Copeland. So it was interesting to see how the deflation of certain eigenvectors helps a lot. But when you go to 3D, do you expect the number of vectors required for deflation to increase a lot?
No, that's exactly true, right? So at high frequency, it's because of the spacing I mentioned, right? In 3D, the eigenvectors get even more closely spaced, and so that's going to be a limitation, right? So we need to think about ways how to potentially overcome that, but it will limit, right? So that is an issue with the method, right? Especially in 3D at high frequency, you're limited on how many eigenvectors you could deflate.
Right.
But we're thinking about, if you got a whole bunch of eigenvectors, I mean, some of them, you can think about maybe compressing them, right? Because a lot of eigenvectors, they sort of have structure. And so Daniel's thinking about sort of some of these techniques for sort of compressing these things. So it takes less storage to, both less storage to store them, but also fewer operations to actually do the deflation with. So there's a bunch of ideas there. But yeah, no, 3D is going to be hard at high frequency.
Right, but just as you showed, the close by eigenvectors look very different. So each will have to be compressed individually, and
correct. But if you look like a high frequency eigenvector locally, it sort of looks like the eigenvector of a square, right? It sort of goes up and down. There's a lot of translation invariance locally to those eigenvectors. You're right. They have to be compressed maybe individually, but there's sort of hidden a lot of structure. That's sort of in the theory of spacing for the eigenvalues, right? It basically says no matter what the domain, you can estimate asymptotically what the spacing of the eigenvalues are, and it's basically the spacing you would get if you solved on a square or a cube. Just because of it's sort of the scale, the difference between the scale of the eigenvectors and the scale of the shape of the domain, sort of roughly.
Yeah, this it's just like Socrates said. It's you can't get out of that difficulty. That's the same difficulty in multigrid for this, right? So in multigrid, this eigenvectors, nobody addresses them. The coarse grid does not address them. The smoother does not address them. If you do deflation, for all of them that are not addressed by smoothing, then multigrid will also work, but that space is huge.
Yeah.
And nobody can, for multigrid to work, it might be much bigger than what you guys are doing. So,
yeah, people use multigrid, but again, as you say, right, the trouble is, quote unquote, low frequency modes actually look high frequency in space, right?
Yep.
Because they're the modes for lambda near omega, so that's a problem.
For the eigensolver, how many eigenvalues and eigenvectors are you computing? Can you compute many of them in the middle, for example, or
yeah, you actually it's relatively more efficient the more you can compute.
Okay.
It turns out. So I think asymptotically, what we at least see computationally, that if you ask for a lot, then it only takes like 2 wave solves per eigenvector.
Okay. All right.
But if you only want a few, then becomes relatively more expensive to
I see.
compute those.
Okay.
So yeah, so that, well, which is good for us, right? Because we actually want to compute a lot.
Yes. Yes.
And so we can compute them all at once. Oh, and it's somewhat, if you have to compute a whole ton, then you can compute a few with this code, and you can do independent solves to get the different eigenvectors you need if you need to.
Okay. Okay. Thank you. Does anybody else have a question for Bill?
Just a small one. Is this, maybe I missed maybe you already said it, but is this code available? Can we play with it, or
You can.
is
So
it
it's
in-house?
it's a little bit complicated because you have to first install Overture, and then you get this code. But the code is available. Well, I'm just switching it over. So it was on SourceForge, but I'm just it's a Git repo, and I'm just moving the Git repo over to GitHub. But if you go to overtureframework.org, it'll point you to the SourceForge. And I haven't updated the SourceForge to point you to the GitHub, but currently they're almost the same. So it is available.
Okay.
But it's a bit of I'm the first to admit it takes a little bit of effort. I have reasonable instructions, but it takes a little effort for it to. Now, if you want, I have a MATLAB code that does these things.
Yeah.
So if you send me an email, I can maybe figure out some place to put the MATLAB code that you could have a look at.
Right. Thank you. Thank you.
Yeah, I mean, obviously we're interested in trying something like that in FEM, and I think the pieces, we have the pieces too, so it's yeah, it's more on the maybe filtering or just your experience with the implicit time stepping. That's interesting.
Right.
Will be interesting for us to try too. I think a lot of the things, just as you said, just work very similarly with finite elements. So and we also can go high order. So
yeah, Daniel, a fellow and his collaborators, they've done finite element methods too. So I'm sure he'd be happy to help. If there are things that you want to know that I'm not familiar with. So, but you're right. It's the basic algorithms sort of you can implement in a day, right? So on a simple code, and then there's lots of details.
I'm sure.
But then there's lots of details.
On existing, it reduces the problem to something else that we kind of know how to solve. So
yeah.
All right, other folks, please unmute, raise your hand. Is your chance to ask Bill. On topics of high order, how high do you guys usually go?
So far for this CG wave, we've just been doing 4th order, but we're working on 6th and 8th. So 8th is sort of for us. 8th is going to be probably good enough. There are issues on overset grids if you go to too high order. Then
yeah. Well, 8 is pretty. 8 is pretty good. Yeah.
But as you know, there's a big jump from 2nd order to 4th order.
Yes.
And then, yeah.
The complexity with respect to the order, what is it? Is it of P to the, I don't know, per degree of freedom or per known? Is it of 1? Is it of P? Is it of P squared?
So let's see. So on a typical overset grid, most of the domain is actually a Cartesian grid. So if we're just doing wave equation, we're just going to use a thin, what I call a thin sparse stencil, right? Like a.
Mm-hmm.
And so
yep,
that'll just scale with P, I guess, right? When you go from 2nd, you'll have a 5-point, and then when you go to 4th, you'll have a 7-point.
So it's all of P per degree of freedom.
Or of P, I guess, per degree of freedom. I think that's probably correct.
P. Oh no, sorry. This is it's in each dimension, right? So it's of P to okay, so in each point it's of P to the D, and you have of P to the D points. Okay.
So the stencil, yeah. So the stencil, you're right. So the stencil width of the stencil is 2P plus 1 to the D, I guess.
Yeah. Yeah.
Yeah. So that's the basic cost increase. Oh no, not 2 plus. It's the sum, right? It's 2p plus 1 plus 2p plus 1 plus 2p plus 1. It's d times.
Oh, it's d times p. Okay.
Because it's a sparse stencil,
It's
right?
a
In
sparse
2D, it's just,
stencil. Okay.
it's
Okay.
just
Okay.
a thin.
Okay.
It doesn't fill in.
Okay.
Of
Good.
course, on curvilinear grids, it fills in. So if you have a big, huge curvilinear grid, it's going to be 2p plus 1 to the d. It will be to the power d. But on Cartesian, that's one event. Yeah. One nice thing
Okay,
about
but so going from second to fourth order is not an enormous cost. Then it's more like
factor 2,
twice.
maybe.
Yeah, not factor of 8. Okay.
No, it's like a factor 2 or something. Yeah.
Stefan has a question. He can't unmute, so I'll just read it. How do you handle material coefficients for dampening materials in the time solver?
So, so in our dispersive Maxwell's equations, which I didn't talk about, we basically augment Maxwell's equations with some extra ODEs. So we solve some extra ODEs. And these ODEs, the coefficients in these extra ODEs are chosen to match a given dispersion relation that you maybe get from experiment or something, right? So, and that can include damping and dispersion and things like that. So they're basically extra ODEs you add in, and we have a technique for it's called a generalized dispersion material model that you can sort of write a general case. You don't have to write like a Drude model and a Lorentz model. You just do this general case.